Hello again and welcome back to the second part of the shortcut course for celestial navigation using this beautiful nautical instrument. So you can take it's very important to have a good shade in front. Then the sun shines onto the first mirror here, and this mirror is called index mirror because it sits on the index arm, and then it reflects through the telescope to the eye. And this mirror here, the horizon mirror, that is semi-transparent. So that means that not only does the sun shine through here via this index mirror, but also the horizon. You see the horizon through there, so they blend, so to speak. They blend so that when you move the index arm here, you move the mirror on top, and that's why you can move down the sun and place it on top of the horizon. And down here you measure the exact angle by the degree, and here the corresponding minute. And you will see that in the practical part, the next part of this course. But now we will go through the sight reduction and the whole idea behind how you can pre-calculate the altitude you should measure if you were where you think you are, and then you compare it with the altitude you actually shot, the HO. You compare them and you notice a difference. So you're not where you think you are somewhere else. You are a bit further away or a bit closer to the sun. And the direction of the sun is called the azimuth. So follow me on the second part to get all these things straight in line and perpendicular when it comes to the position line.
So now comes part 2. So we have had a lot of theory, so we know now how we get to the HO with these corrections thanks to my template. So now let's fix a position. We'll go back to where we came from. We are here, the sun is there. What we can do is we can measure the zenith distance, which is nothing else but 90 degrees minus HO. We get a position line, that's the orange dotted line in the right angle to the yellow azimuth. We wait until the afternoon and then we get a second distance. And now comes the very practical thing that was invented by the Americans actually in the Second World War, when they quickly had to determine their position while flying with their big bombers over the Atlantic to Europe. So they invented this idea of having pre-calculated altitudes at a lot of positions on the Earth. And the pre-calculated altitudes are called HC. So all then later you have to do is actually to compare your observed altitude with the calculated altitude. Let me give the whole idea. So here we are, there is the sun, and now let's assume that we have a latitude and a longitude, that we know that. We want to know what is the altitude we should measure at this position. Okay, then we take the position of the sun. It has a declination and a longitude that we haven't mentioned yet. So we haven't spoken about how the sun is moving from east to west yet. We've only looked up the declination. So when you move from east to west, you have to have a reference point, and you take the reference line the same as you have and we have for our longitude. It's the Greenwich. That is the one where which goes through Greenwich, the meridian outside London. So the longitude of the sun is called the Greenwich hour angle, GHA. So the declination is the latitude and the Greenwich hour angle is its longitude counted westbounds. So the Greenwich hour angle starts at 0 at the meridian, goes westbounds, has 180 degrees on the other side of the Earth, but continues then 190, 200, 210 degrees until it goes back to Greenwich with 360 degrees. So now we can determine the position of the sun if we again look in the almanac. So here we have the almanac, the same page as we had before, the 15th of June, and then we have the different hours. And in this case, we look at the Greenwich hour angle. The declination was to the right. And you can see how fast it moves. You can see that it actually is 15 degrees for an hour. So between 3 and 4 o'clock here, it has moved another 15 degrees. So that's 15 times 60 nautical miles. So that's a huge distance. The sun is really fast. So interpolating this, you could do that, of course, by means of a calculator or a lot of head count. And you can't do it by eye at all. So instead, you take the Greenwich hour angle for the preceding hour, and then you add the increments. How much more has it moved after the last full hour? So what you do is that you look at the increments page for the minutes and seconds that you shot it. Minutes and seconds. Here is the increments page. It's in the back of the book. And if you zoom in there, you can see for 53 minutes and 4 seconds, for instance, the sun has moved on 13 degrees and 16 minutes. It's just a way to make it easy for you to calculate the Greenwich hour angle for the exact time as you shot it. So first you take the Greenwich hour angle for the full hour preceding, and then you add for the minutes and seconds. Here, 53 minutes and 4 seconds, for instance. So that's how you do it. So by doing that, you have the exact position of the sun. Hooray! You have the declination and the Greenwich hour angle read out of the almanac. Let me now explain how the book is being built up. The book where the pre-calculated altitudes are being found. It's called a sight reduction table. So we are here and the sun is there. And we're talking about what angle we could measure the sun when we are here and the sun is there. But where is here and there? Well, we could be in the Mediterranean and the sun is over the Red Sea. But we would measure exactly the same angle if the sun had been over, well, Africa here and we somewhere on the northern Atlantic. Or the sun is in the southern Caribbean and we are in Bermuda. The angle would actually be the same if we mirrored the whole idea and put the sun over here. Because if the distance is the same, the relative distance between us and the sun, then the angle would be the same irrespectively if the sun is the same amount east or the same amount west of us. And we could even put the whole thing upside down. So if the sun is here and we are there, then it's also the same angle. So it has to do something with the relative position of the picture point of the sun and us. Well, we can say my latitude and the sun's latitude, called declination. That is very important, right? So that's why the sight reduction table uses your own latitude and uses the sun's latitude, the declination. So, but you need to know something more. You need to know the corresponding longitudes of us and the sun. Well, we can say that my longitude is one thing, and the sun's longitude, which is called the Greenwich hour angle, is another thing. And now the book is made for the relative position of us and the sun. So the relative position of our longitude and the sun's longitude, that is called the local hour angle. So that's the difference between our longitude and the Greenwich hour angle. And how do you calculate that? If we are on western longitudes, and that's what this course is about, then you simply do the following. You take the Greenwich hour angle and deduct your own longitude. And then you get the local hour angle. Now the book can't have infinitive numbers of positions for which the calculated altitudes are given. So it only has a limited, but very many, I can say. So for which values is the book printed? It is printed for the full degree of my latitude, any sun's declination by 1 minute exactly, and the full degree of the local hour angle. So since we can't change the sun's longitude, we can maybe amend our own longitude a little bit, because it's just an assumption where we are anyway, in order to get a full degree of local hour angle. That's the secret. And I know that you don't really think that this is very easy to understand, and maybe you've lost the track now. But the more you listen to it, the more you do it, the more it becomes natural that the local hour angle is the difference between the sun's longitude, called Greenwich hour angle, and our longitude. And this needs to be a full degree so we can use the tables. Okay, so back to our position here. So we want to know the sun's position. We have that at a specific time, and then we know that we can pre-calculate the altitudes and the direction to the sun. And how this is done, this is shown in my longer video, but just believe me that you can do it. So you can do it for many points. Here, if you can do it for these points, you can do it for even more points. And as I just said, the points that they are using in this sight reduction table is for a whole degree of the latitude, the sun's declination, and the whole degree of the local hour angle. That's what you can find in the book. So you think you are where the red boat is. That's your estimated position. And then you take the closest point for which there is data in the book, which is called the assumed position. That's the white dot. So in a nutshell, what you do is that you have your estimated position of the red boat. That's where you think you are somewhere. Now choose one which is as close as possible to your estimated position, but use one for which data can be found in the sight reduction table. So find a point, find a position close to you where you have a full degree of latitude and where you have a full degree of local hour angle. And the sun's declination is just taken from the book. Let me explain it in another way again. So let's assume you're on your way to London and you have a milestone. It says 356 miles still to go to London. That's the distance to London. And then you have another milestone where it says 355 miles to London. So let's assume that we think that we are here at the London at this point where it says 355 miles. That's our assumed position. So we look up, that's the point that we can find information in the sight reduction table. So we look up the direction of towards the sun and the altitude that we should be measuring this coconut tree. Remember the coconut in the beginning. So that's the sun. So it says this is how high up, the altitude, the angle I should measure the coconut. Now, if I actually do measure something bigger, well, I'm closer to London. I'm closer to the coconut tree, right? And if I measure something smaller, I am further away from the coconut tree. Then you can draw a position line. Somewhere on this line I am. And the distance that you are further away, that is called the intercept. So these are the typical words, the vocabulary used by a celestial navigator. So we have the picture point, we have the sun here, and it has a picture point on the surface of the earth. And somewhere we have an assumed position. That is the position closest to us for which we can find in the book the azimuth, which is the direction of the sun, and the calculated altitude. So for this assumed position, we can find the direction of the sun, because that is printed in the book, and the altitude for which we should see the sun. Now we use the sextant, and we have an HO, an observed altitude. And let's assume that the observed altitude is smaller than the calculated altitude. Well, then we must be further away than the assumed position, because if we measure something smaller, if we are further away. So now we just compare these two. Let's assume that the calculated altitude, which we find in the book, should be 42 degrees and 55 minutes. And the observed altitude, what we really measure, is 42 degrees and 39 minutes. Well, the difference is 16 nautical miles, right? So that means that the intercept, how far we are further away from our assumed position, is 16 nautical miles. And this is where we should draw our position line. And that is what you draw on a chart. So the great solution here is that you don't need a chart where the picture point of the sun and our position are both found. Instead, you can have the chart inside the box where only the assumed position, which is close to us anyway, and our position line fits. So we just need a little chart. This is a big blue planet, so let's zoom in and take this little chart. So let me explain the whole thing again, because it's always the same thing shown in different ways. Here we have a little chart. On this chart, we need to have the possibility to draw our assumed position. Then from the book we can find the azimuth, and by comparing our observed altitude with the calculated altitude found in the site reduction table, we can then take the difference, get the intercept. In this case we are further away from the sun, and here this is where we have our position line. On our blue planet it looks like this. So that was the same thing. Now let's move on in the afternoon and let's get a second position line and then the fix. So then in the afternoon we get a second assumed position, again an azimuth and an intercept, which is calculated by comparing the two angles, the one that we should have measured and the one that we actually measured, and we get a second position line. Now where they cross, that is not really our fix, because as everybody knows, you have continued to move. So that's why we have to move the first position line according to our course and distance. So what you do is you take the first position line, you transform it, you move it, and that's the fix. Let me tell you the same story from a new angle. So what you need is an assumed position. You need to know somewhere where you are, preferably a position for which information is found in the site reduction table. And then you need an astronomical almanac. In that almanac it says at what time the sun has which position. It gives you the declination and the Greenwich hour angle. So you need a clock. You need a chronometer, and by using this clock you can then look up the position of the sun, declination and Greenwich hour angle. So here it is, the fixture point of the sun, where the beam goes through the surface of the Earth in a 90-degree angle. Now, had we been here exactly on this picture point, well, we would have had 0 nautical miles as our zenith distance. We would be exactly where the sun is, and we would measure 90 degrees. And if we measure a bit less than 90 degrees, well, we would be a little bit further away from the picture points of the sun. Here is our observed altitude. And what we know is that we are somewhere along this line, along this position line. Somewhere. We don't know exactly where we are, but we know that we have a certain distance to the sun. And the distance is 90 degrees minus the observed altitude. Okay, we're not so close to the sun, we're over here. So the whole idea is that we have a site reduction table. So for some smart positions, a whole degree of our latitude and a whole degree of our local hour angle, remember, these are the positions for which the site reduction tables have information. And the site reduction table gives you the direction of the sun, which is called the azimuth, and the altitude, which you should be measuring the sun if you had been on that assumed position. Well, you measure something on the sextant, then you do some corrections, and you get an observed altitude. So the observed altitude is not exactly like the calculated altitude. Had it been that, then you knew that you were exactly at the assumed position. But in this case, you measure something smaller, meaning you are further away from the assumed position. You glide along the azimuth, either closer or in this case further away. How far away? Well, that's the intercept. It's the difference between the calculated altitude and your observed altitude. Let's assume it's 18 minutes of a degree. And the great thing is, minutes of a degree can be translated into nautical miles. So you're 18 nautical miles further away. Somewhere on that semicircle, somewhere on this position line. Well, the calculated altitudes and azimuths can, of course, also be obtained from a computer program. And the good, simple thing is that you can just use the app, and then you can enter your own position, and it calculates, this app calculates what altitude you should measure if you were where you think you are, and the azimuth. But I think it's much more beautiful being able to do it with pencil and pen and tables only, and not using anything electronic. So that's why you need the sight reduction table. It is made for the whole number of latitudes, of your latitudes, the whole number of local hour angle, which is the difference between the sun's longitude and your longitude, and the real declination of the sun. And out comes the azimuth and the calculated altitude. So in a nutshell, you're proving that you are not where you think you are, and then Astro gives you the exact measurements of your misjudgment. Now let's start. We have a to-do list, don't we? It goes in 5 simple steps. Step number 1, that has to do with angles and time. So you note down the exact time in UTC, hours, minutes, seconds. And you don't note down the angle that you have measured on the sextant. Step number 2, look up the position of the sun at exactly that time that you shot the sun. Then you need to choose an assumed position. That's picking a position which is as close as possible to where you think you are, but for where there are data in the third step in the sight reduction table. So as third step in the sight reduction table, for that assumed position, you find the pre-calculated altitude, HC, which you should measure if you had been at that position, the assumed position, and the azimuth, the direction of the sun. Step number 4, you calculate the intercept. The intercept is the difference between the observed altitude and the calculated altitude. And if you observe something that is smaller than you should, then you're further away. And if you observe something that is bigger than the calculated altitude, you are closer. How much? The difference between those two. And then you draw it all into your chart as step number 5. What do you draw? You draw your assumed position, you draw the azimuth, the direction of the sun, you draw the intercept, and then you get the position line. That's what we want to get. So these 5 steps are all found in my template. So this template looks a bit complicated, but if you look up on the left top corner, it says number 1 next to the sextant there. So the first column is step number 1. The second column is all about the blue book, all about the almanac. Step number 3 is all about the sight reduction table, finding the azimuth and the calculated altitude. And then step number 4, which is to the very right, there you compare the both altitudes and you get the difference between these two, which is the intercept. And as soon as something is red here, you see the on step number 2, the red latitude of the assumed position. It drops down into the step number 5, namely for drawing into the chart. Under step number 2, you go further down, you get the longitude of the assumed position, also a red figure. So that also goes down in step number 5. So in the end, you only use what is in the bottom right corner in that red box. These are the things you draw into your chart. And we will go through this on our way from Galicia to the Azores in a separate video, hands on. Remember in the beginning when I said that it was very difficult to draw something on a chart where the picture point of the sun and our position both fit into this very small scale chart. So we need a large scale chart. And the large scale charts for the Atlantic, well, it doesn't make sense to have charts with just water and water and water and water on it. So that's why you draw your own chart. So you pick the latitude for the latitude of the assumed position. In this case, it's 42 degrees north. So the center horizontal line, that's your latitude for 42 north. That's where you are somewhere. And to make things a little bit more chart-like, we'll draw 2 latitudes more, one south of us and one north of us. And since we are in the northern hemisphere, 41 goes down here and 43 goes up there. So these are the 3 lines for the latitudes. That's easy. Now with the longitudes, we only have 1 line. We'll pick that line in vicinity of our assumed position, where we want to be drawing our position and the azimuth and the intercept and moving the position lines and things like that. So in this case, I'll say it's 19 west. So this is my plotting sheet with 19 west, but it only has 1 longitude. The other 2 longitudes, well, on western longitudes, you know that west increases the numbers if you go to the west. So 18 west is to the east of 19 west, and then 20 west is to the west of 19 west. So these are the 3 figures of the longitudes, but there's only 1 line. So we need to draw 2 more lines. And since this is a Mercator projection, every chart used in the marine field is Mercator projection for navigation, we need to draw this line depending on our own latitude. Because the distance between longitudes are not the same on the Earth. So the more close to the equator you are, the bigger the distances between the longitudes. And the more you go towards the poles, North Pole or South Pole, the more you go to the North Pole in this case, the more narrow the 2 longitudes to become. And that's why we have the scale to the very right bottom there. So this scale is your longitude scale. So the scale is dependent on your latitude. So we are on 42 north. So we follow that down here, 42 north. So this is the distance valid for 42 north between 2 longitudes. So we take the divider, measure that distance between or for a degree, move it over here and draw the first line there. So this is the first longitude. And the same distance, of course, is valid on the other side towards 20 west. Now my chart is ready. If you are a bit observant, there is a second method to draw the distances of the longitudes, and that is by using the figures on the outer circle here. So that means that you go along 42 north and follow these figures. So it's no coincidence that the longitude of 18 west intercepts the circle just at the figure 42, which is your latitude. So whichever method you use, it's fine, as long as you remember any measurements of the longitude is done along the scale on the right bottom corner, and any distances are only measured along here, along a longitude, just like a normal chart. So this was the theory. So what do we do now? Well, now you can go and jump into part 18 to watch it in real, where I do a real sun run sun, and you can see me doing all these calculations on board Regina Lasca on my way with my two friends from La Coruña to the Azores. And part 19, that's when my guest Nick is doing it himself, and this is a typical example of how celestial practical navigation is being done on Regina Lasca. So that's what you can do as a next step. Watch the real thing after having seen the theory. And if it's all too complicated for you and you still want to learn, just join an ocean course in Malta and look it up at reginasailing.com, and then you may have it step by step with a lot of time to explore it by yourself in classroom in 6 wonderful fun days on the sunny island of Malta. So maybe see you there. Otherwise, enjoy the full course, also available on my website.